This video is the report of two experiments, DC servo and the STIG. Let's talk about the DC servo experiment first. This laboratory is based on the simple DC servo, and there's a first-order dynamic between the voltage supply and the rotational speed of the motor. Both MATLAB simulation and the real hardware are tested in this experiment. This slide shows the user panel of the MATLAB UI for DC servo. On this panel, you can change the input voltage to the DC servo motor from negative 10 volts to 10 volts. You can also see the rotational speed on the middle of this panel. By pressing Put Velocity Reading into graph, you can put the data of velocity to the graph and then plot a curve, which is the velocity versus input voltage. And then the slope of the curve will be calculated by MATLAB and shown on the graph. This slide shows four different situations when the input voltage is 0 volts, 1 volt, 2.2 volts, and negative 2 volts. We can see that when the magnitude of the voltage is less than 2.2, and the velocity of the motor is 0. If we change the magnitude of the voltage to 2.4 volts, then the motor begins to work, and the rotational speed is shown on this panel. From the figure on the right, we can see that when the magnitude of the voltage is smaller than 2.2, the rotational speed is 0. And when the magnitude is larger than it, the velocity is proportional to the input voltage. And then the slope of the curve can be calculated from the left figure, since the data with 0 velocity will influence the calculation of the slope of curve. Therefore, the gain of this system is about 0.74983. After finish the simulation on MATLAB, let's move to the hardware experiment. The hardware experiment is done with the LabVIEW programming software. By turning the knob on the user panel, the input voltage to the DC servo can be changed. The data for the positive input voltage will collected first. As shown on the table, the first line is the input voltage, the second line is the speed sensor output voltage, and the third line is the rotational speed of motor. We can see that the motor will not rotate when the input voltage is less than 2 volts, and the rotational speed will become faster when the input voltage increases when the input voltage is larger than 2 volts. After the data were collected, two diagrams were plotted automatically. One is motor speed versus speed sensor output voltage. The other is applied voltage to motor input versus motor speed. And then do the same thing with negative input voltage. The second experiment on DC servo is to find out the time constant of the response by looking at the step response of the servo. The time constant of this response is 1.646 seconds. The third experiment of DC servo is to use the gain, which is calculated by multiplying the slopes of two diagrams in experiment 1, and the time constant to find out the time response graph and transfer function of response. The time response graph and transfer function are shown on the screenshot. The STIG experiment. This laboratory combines an understanding of DC servo dynamics with feedback control. Students will observe dynamic response and how these are affected by the choice of feedback control law. There is also an opportunity to see how real-world equipment may not behave in the same way as an idealized transfer function model. First, we use MATLAB to simulate this experiment. When I keep integral gain to 0, and only change the proportional gain, as the screenshot shows, when the proportional gain increases from 1 to 5, the steady state of the response will increase. Furthermore, the response speed and overshoot will also increase with the proportional gain. Then keep proportional gain stay at 5 and change integral gain instead. From screenshot, we can find that the response curve is expanded vertically. The steady state gain increases with the integral gain, but the response speed and the time to reach peak point still not changed. After change the proportional gain and the integral gain several times, the perfect response appeared when the proportional gain is at about 1.6. The integral gain is at about 0.5. The hardware experiment is also done on LabVIEW. By input the proportional gain and integral gain, the car will move along the rail. In hardware experiment, the perfect response can be get when the proportional gain is at 5 and the integral gain is at 70. The following video shows the movement of the car when the parameters are 5 and 70. The car is at 2 at beginning and it's back to 2 after the response finished. After that, the proportional gain is changed to 6 and keep the integral gain at 70. We can find that the response speed increases and the steady state gain increases as well. Then keep the proportional gain at 5 and change the integral gains. We can find that only steady state gain changes, and the other things like response speed do not change. Compared with hardware experiment and MATLAB simulation, the results of influence of proportional gain and integral gain to response are similar between hardware and animation. The only difference is that there are some fluctuates after the response reached to the steady state gain in the MATLAB simulation, but it does not appear in hardware experiment. I think that this is because the existence of friction force in hardware experiment which acts like a damp.